Hello, Mr. Eric, Mr. Ryan. It's Friday again. Okay. So on day 678, we talk about this packing the apples. So we given the apples in different packs. 1 apple in the first pack, 3 apples in the second pack, 2 apples in the third pack, and we're given a few boxes. Each box, the numbers on each box, meaning that the maximum number of apples it can pack. For example, we can put 4 apples to the first box, 3 apples to the second box, etc. Okay, the apples in each pack can be packed into different boxes. Okay, so on day 678, we say the strategy is to choose the box which has the most capacity, first, right? Because we can repack those apples. So, those numbers on the apples, we can just put it together. We can, first of all, we can unpack all the apples into just one, we just put it on the table, right? So for example, like we have 6 apples, 1 plus 3 plus 2. So we have 6 apples, we just put it on the table. And then we sort the box, okay? We sort the box in the capacity from the largest to the smallest. So 5, 4, 3, 2, 1. Okay? Then we first choose the box of 5, and then we start putting the apples. We start moving the apples from the tables and then to put it on the current box. And if the current box is fulfilled, is complete, then we move to the next box, which is 4, right? In a descending order. Okay, so this is the code. First of all, we sum all the apples, which is 1 plus 3 plus 2. That's 6. Now we have a check here. If we have more apples than all the boxes capacity, right? For example, if we have 6 apples and the maximum number of apples we can put in a box is 5, then apparently this is a mission impossible, right? So we simply return -1. Otherwise, we saw the capacity in the descending order. Why we still have apples? Then we check if the quantity of current apples is more than the capacity of current box, which is the index I, right? Apple minus equals box I. What does it mean? If apple bigger than box I, then apple minus box I, meaning that we put the current apples into this box, and then obviously I plus equal 1, meaning that we need to move forward to the next box. If it's smaller, okay, so if it's smaller or equal, then we don't need to move to the next box. So basically, if it's smaller than the box I, meaning that the current box, we can put the remaining apples into the current box and return I plus 1 because the index starts with 0, and we need I plus 1 box. Okay, so we analyze the time complexity. This one, okay, so we talk about that. This is n if the number of the apples is n, if the number of boxes is m, okay?
What does
So,
M mean? It's
okay.
a
Just to,
accent, I think.
okay. So this is on, okay, and this is om. This is on, om, and sorting is om log n, right? And then this one, right? We talk about that. This one, in the worst case, all the numbers will be exhausted from the box, right? All the numbers will be exhausted from the box. So OM, right? So the time complexity is OM plus 2M plus M log M, right? This is trivial compared to that. So the time complexity is OM plus M log M, okay? Last time we talked about least bit, right? So least bit is actually OM. We can make it faster by binary search. So if we saw the box, then in a descending order, is it like 4, 3, 3, 2, 1, right? Yeah? So look, this is 6, right? We have 6 apples, 6 more than 5, right? So we use the first box and we move the second one. Remaining is 1 apple. The second box enough to hold 3 apples, then we stop here, right? How about if I convert it to list? Can you tell me what's this? 5, 9, 12, 14, 15. So what's this? So So this is a box, and I get this. What's this?
It's just like adding all of the
What? How do we get the 9?
5 plus 4.
How do we get the 12?
9 plus 3.
14.
12 plus 2.
Okay, yes, that's good. So that's the prefix sum. Okay, prefix sum. So we just adding that prefix sum accumulated, right? So 5 is the sum of the elements numbers up to this point. 9 is the sum of the original array up to this, right? So it's the sum of these. 12 is sum of these. 14 is sum of these. 15 is sum of these. So this is quite useful because every time we go through from the left to the right, we can just accumulate, right? So when we get to this point, 12, how do we get a 12?
9 plus 3.
Yeah, 9 plus 3 because we already know that it's 9. 9 plus 3, right? 14 is 12 plus 2, right? 15 is 14 plus 1, right? We don't need to, we don't need to calculate like 5 plus 4 plus 3 again, right? Because we already know the previous sum, right? Okay, this is one trick to attempt the prefix sum. And then we can use the accumulate. So accumulate function, right? Accumulate a box and convert it to a list because accumulate returns an iterator. We convert it to a list and this will be the array. So why this is useful? So coming back to the original question, we have 6 apples. Looking at this array, how many boxes we need? We have 6 apples. How many? We have 6 apples. This is the box capacity. How many boxes we need?
1, 2.
2. Why is it 2? Why is it 2? Why is it 2?
Because...
Remember the original question, original array.
Yeah, I know.
So why is it 2? 6. Why is this 2? Come on. Hmm?
Because 6 divided by 5 is 1, but you have 1 remaining apple, so...
Yeah. This is the original way, right? That's good. But looking at that, okay, I have 6 apples. So if you look at this, how many boxes do I need? It's the same, right? 2, right? Because here it's 9. Okay, I have 13 apples. How many boxes I need? Without looking at it. How many boxes I need if I have 13 apples?
3.
How is this 3?
What?
Why is this 3?
Because
13,
okay. Divided by...
13, okay? 13 minus 5, 8, minus 4, 4 minus 3, 1. I have 1 more. Needs to go into the 4th box. Do you get it?
No.
I have 13 apples, right? And then these are the boxes. 5, 4, 3, 2, 1. The first box, this argument, right? The first box, 5 apples. So, minus 5. The second box, 4 apples, minus 4. The third box, minus 3. So what's remaining? 1 apple, right?
Okay.
1 apple needs to go into this one, right? Okay. So
Okay.
you get it right? So okay, 13 apples. How many? How many boxes? 4. Okay, good. Okay. 11 apples. How many? 11 apples. How many boxes? By looking at this, 11 apples. How many boxes?
3.
10 apples. How many boxes?
3.
Good. Okay, 14 apples. How many boxes?
4.
Good. This is prefix sum. So basically, we need to find, for example, like 13, right? This 13 is this one. We need to find the position where we can put the 13 in this sorted array, right? This is sorted, right, from the smallest to largest, right? So we can binary search this position. Remember, we can use the byset. That's why this whole thing here converts to these 2 lines of code. And these byset, okay, byset this array, this is O log n. Okay, so instead of log m here, we use the binary search to reduce the time complexity to log m. Okay, so why? Remember that the byset thing. 2, 2, 2, 3, 3, 3, 4. 3, 3, 4. Okay? So this is a sorted array. Okay, so this is a sorted array. Let me get this, okay?
Oh.
This is sorted array, okay? Once it's sorted, we can binary search, remember? Yeah? We can binary search in a sorted array. Are you with me? Yeah, we can binary search. What's binary search? Remember the thing? 1, 2, 3, 4 up to 100, right? You check the middle. If it's smaller, you go the other half, right? Yeah, that's binary search. I have a number in my mind from 1 to 100. Guess.
70. 35. 50.
That's not a strategy. Yeah, 50. Go with the middle. 50. Okay, then I say.
No, I bet it's not 50.
Good. Okay, so it's smaller than 50.
37. 25.
Okay,
22.
good. Yeah, you know that, right? It's always in the middle because in this case, in this strategy, you can always narrow down the search space in half, right? Every time, look, every time you drop half, right?
You can risk.
Okay, so this is 50, right? If I say smaller, then you go this 25, right? What happened to these numbers, 51 to 100? You don't need to consider, right? Because I just told you it's smaller than 50. You don't need to go there. Binary search tree, remember?
No. What if you don't say if it's big or smaller?
That's very good question. Why, if I don't say smaller or bigger, then that's no use, right? Because it's sorted and I can, feed you back with this information and you can base on this information. Just imagine this is a binary search tree. I remember binary search tree. The nodes on the left are smaller. The nodes on the right are bigger, right? The same thing. Bicep left array, if we say 2, okay, we want to find a 2. So then it will return this position. All the previous are strictly smaller than 2, okay? But if it's bicep right 2, then it will return this position because all the previous can be smaller or equal, and all the elements from this point should be strictly bigger. Okay, so this is the difference between bicep left and bicep right. We talked about that a long time ago. So here, why can we use it? Coming back to this, right? From here to here, right? Remember, this is the box sorting in the descending order. And we do this accumulated sum, prefix sum. So it becomes 5, 9, 12, 14, 15. What's so special about this number? 5, 9, 12.
You can just find your number.
That's right. These numbers are increasing, right? It's increasing. It's become bigger and bigger, right? This is ascending order, right? It's in order, right? It's sorted. Okay, it's sorted. And then each number is the accumulate sum from the start, from the first box to the current box, right? So let's say if we have 11, okay, if we have 11 apples, then we say we find a position to put the 11 here. Where do we put the 11 in this array? If we want to make it sorted, look, this is a sorted array, right? I have a 11. Where do I put it?
3.
In between 9 and 12, right? I need to put it here, right? Yeah? Okay. And this index is 0, 1, 2 plus 1, right? So we need a 3 box. 13 apples. Where do we put it?
Between 12 and 14.
That's right. Here, right? Okay, so now we know how many boxes because once we put it, we know how many numbers before this number, right? Simple. This is binary search. Remember this algorithm, right? We have 13 apples. We try the first box. We have remaining, then we move to the next box, right? We try one by one. But from this one, we use the binary search using the bicep. This is O log m. So the time complexity for this one would be OM plus M plus log m, okay, plus M log m. M and log m compared to M log m is trivial, so we can drop these two parts. So time complexity is still OM plus M log m, okay? However, if we implement it, because this part is practically faster, okay? So to sum up, what have you learned today?
So we have apples and we want to fit them into boxes.
Yes.
Starting from the left, and you have to fill them up. You have to fill starting on the left, and you have to you can't switch boxes until you finish that one, and then you go to the right.
Yeah. What's the improvement today? What's new today? Because we in 6-7a we talk about the same problem, but today what's new?
We have this thing called
Accumulate.
Yeah.
Prefix sum, and then
because it shows It shows the amount of apples needed. It shows the sum of the apples needed for a certain box, and the second one shows the sum for the first 2 boxes, and then you just can put your numbers on the line.
Okay, that's it for today. Bye bye.
Bye.
Bye.